Good morning, students. Yesterday, about noble gases introduction and some important points about noble gases. And first prepared noble gas compound explained by Ian Bartlett. So there are preparation methods of noble gas compounds like xenon compounds. Here, xenon and dioxazine both are having a comparable ionization energy. So these two are both are having a comparable ionization energy. Due to these comparable ionization energies, your dioxazine forms O2PT EF6 one complex like. Now this dioxazine ionization energy is 11,570 kilojoules per mole amount of energy required to liberate one electron from that molecule. So after this simple complex compound formed by the dioxazine with PTF6, Mr. N. Bartlett conducted so many experiments in the laboratory and finally succeeded to prepare the first noble gas compound by N. Bartlett because this xenon also having that ionization energy is 1175 kilojoules per mole. So after the so many experiments, Mr. N. Bartlett conducted so many experiments and finally succeeded to prepare some noble gas compounds because dioxazine and xenon both are having comparable energies, and immediately Mr. Bartlett conducted so many experiments. This is dioxazine and xenon both are having comparable energies. Dioxazine forms like compounds, why not xenon? So on the basis of simple question, he conducted an experiment, that is xenon is reacted with PTEF6, it gives XePTF6. An orange red crystalline substance is formed. So this is the first prepared noble gas compound. Yesterday, preparation method and some important points explained to you. So the first prepared noble gas compound by N. Bartlett is nothing but XePTF6. That is Xenon Hexafluoride 5. The oxidation state of platinum is +5 here. In this case, oxidation state is +4. Both are very, very important IUPAC names. So after this first prepared noble gas compound XePTF6 by N. Bartlett, so many experiments conducted by so many scientists. Finally, xenon combines with high electronegative elements like fluorine and oxygen only. So are the xenon combines with highly electronegativity elements like fluorine, it forms XeF2, XeF4, XeF6 like hexafluoride, tetrafluoride, difluoride, fluorides of xenon, oxides of xenon, XeO3 and XeO4, these are the oxides of xenon. Oxo acids of xenon like XeOEF4 or XeO2EF2 like XeOEF2 like some important oxo acids of xenon. Radon is a radioactive element, disintegrates, rarely available. We can't isolate. But here the krypton forms only one type of krypton compound with fluorine, that is F2. It gives here the KrAF2, krypton difluoride. Now remaining helium, neon, argon, these three elements right now there is no such a helium, neon, argon compounds with fluorine and oxygen. That's why xenon only most important noble gas element which forms different compounds with the fluorine and oxygen. Krypton only one, radon do not. And helium, helium, neon, argon do not form any any noble gas compounds. Noble gas compounds are not formed by this helium, neon, argon. So on the basis of this, here are some important preparation methods of xenon compounds, like first one is XeF2. So the direct combination of xenon vapors with fluorine vapors gas, and it is gas. At 673 kelvins, this xenon is in excess, then it gives XeF2, xenon difluoride is formed. Similarly, your xenon tetrafluoride, that is xenon reacts with fluorine, that is a ratio is 1:5 ratio. Now this is at 873 kelvins, it gives XeF4 is formed, xenon tetrafluoride. Now here the xenon hexafluoride, this is also Xa react with 3 moles of AF2, that is ratio 1:20 ratio at nearly your 573 kelvins, then it gives XeF6, xenon hexafluoride. Similarly, this is XeF6. Your XeF6 xenon hexafluoride also prepared by using your xenon tetrafluoride. Reacts with O2EF2 at 143 kelvins. It gives XeF6, xenon hexafluoride plus dioxygen is formed, plus O2 is formed. So these are the some important direct preparation methods of difluoride, tetrafluoride and hexafluorides of corresponding xenon compounds. Xenon difluoride, xenon tetrafluoride, xenon hexafluoride by like direct xenon with fluorine, and also combines with oxygen, or a combination of both that gives fluorine and oxygen and gives both oxyfluorides, xenon oxyfluorides. Anyhow, to obtain these compounds, xenon compounds are colorless, tasteless gases. They are readily sublimizes, converted into vaporized molecules. The obtained XeF2, XeF4 and XeF6 are colorless and tasteless gases, and they are readily sublimizes at 298 kelvins. Readily sublimizes means readily vaporizes, direct converts solid into gases at a room temperature. Now these are readily soluble in water, and it gives corresponding compounds. First one is here XeF2, is soluble in water. It gives the 2Xe plus, take 2 moles, 2 moles plus 4 HF plus oxygen gas is liberated. Xenon difluoride, when dissolved in water, it gives corresponding hydrogen fluoride, HF, and oxygen gas is liberated. Whereas XeF4 is reacted with water, it gives xenon plus, xenon trioxide plus, hydrogen fluoride plus oxygen gas is liberated. Along with this xenon, xenon trioxide also form. This is one of the most important preparation method of xenon oxides. Take here the 6 moles, the 12 moles. Your hydrogen fluoride 24 HF. Now here the oxygens are here 12 are there. Take here the 6 are there. Take here the 4 moles and here 2 moles. The remaining here 6 moles of oxygen gas is liberated. Now here the XeF6 is reacted with the water. It gives your Xe4 is there here. XeOF4 plus the 2HF is formed. Xenon Tetroxide. Oxyfluorides are formed. These are very, very important, 3 important reactions. On hydrolysis of these 3 compounds, what are the products? Complete hydrolysis, it gives corresponding compounds. These are the some important chemical properties. Chemical properties of these xenon compounds. Xenon difluoride, xenon tetrafluoride, xenon hexafluorides. These xenon compounds are acts as a fluorinating agents. Xenon compounds are the xenon compounds XeF2, XeF4, or XeF6 acts as an fluorinating agents. Fluorinating agents, all these 3. Now here XeF2 reacts with the phosphorus pentafluoride. Now this phosphorus pentafluoride acts as a fluoride acceptor. It is fluoride acceptor. It is ready to accept fluoride ion from XeF2. It is F minus donor. It is donor. Then it forms your XeF. After donating, it becomes plus. After accepting, it becomes a negative, like minus. Now this is a cation. It is a anion. It is like here the XeF4 reacts with the Sb5 F5. Then it gives XeF3 cation complex and here SbEF6 power minus 1. This is also a acceptor. It is fluoride acceptor. So one of the most important question maybe they'll ask based on this in objective, and our textbook given one simple word given. When these xenon compounds reacted with the fluoride ion acceptor, then these xenon compounds are exist as cationic complexes. So the acts as a fluorinating agents means here in this case the fluoride ion donors donated to the fluoride ion acceptors. So the phosphorus pentafluoride ready to accept the fluoride ion and becomes an anionic compound is formed, but the xenon compound becomes cationic in nature. It is a cation and it is a anion. Whereas xenon hexafluoride reacts with the sodium fluoride. Now, in this case, this is different. This is the F minus ion donor. It is when xenon compounds react with the fluoride ion donor. In this case, it acts as an acceptor, like it is F minus ion acceptor. In such cases, fluoride compounds forms anionic compounds like. Now it forms like Na plus into XeF6 power 1. This is the anionic complex is formed. So these are very, very important. It is a cation, that is a sodium. Not only sodium fluoride, any monovalented MF like this, +1 oxidation state, like sodium, potassium, rubidium like this, metal fluorides are ready to donate fluoride ions. So whenever xenon compounds reacted with the fluoride ion donors, then it forms an anionic complex. Same xenon compounds react with the fluoride ion acceptors, it forms a cationic complex. In our textbook, in one corner given these 3 examples. In one example only, in this common example only given all these. Better you read this fluorinating agent example. With the XeF2 and XeF4, these 2 are fluoride ion acceptors. The xenon compound forms cationic complex. Xenon hexafluoride react with the fluoride ion donors, then it forms a anionic complex of the xenon compounds. That is the main difference between these. Okay. So are the preparation methods of xenon fluoride compounds, and there are some important properties. Physical and chemical properties completed. The next one is xenon oxide compounds. Xenon oxide compounds. These xenon oxide compounds are here mainly XeO3 trioxides. This is xenon trioxide, and another one is xenon tetroxide. Xenon tetroxide are the 2 important oxides of xenon. So already under chemical properties of xenon fluoride compounds given on hydrolysis of xenon fluoride compounds gives xenon oxides. Xenon oxides like your XeF4 already given is reacted with water. This is 6 moles and this is 12 moles. Already given this reaction. Hydrolysis of xenon tetrafluoride gives corresponding xenon plus here the xenon trioxide, here the 3 moles, sorry, it is 4 moles of xenon trioxide plus here the 24 HF hydrogen fluoride plus oxygen gas is liberated, that is the 6, 12. How much? 12, 6. How much? 2 XeO3. Now here 4, then it is 3O2 balanced. Now it is 2 XeO3 is the oxygen trioxide is on hydrolysis of these. Also here xenon hexafluoride react with water, it gives like XeO3 is formed. Here are the 3 moles. Then here XeO3, then 6 plus 6 fluoride ions are there like 6HF. This is the xenon trioxide. So by the hydrolysis of complete hydrolysis of xenon tetrafluoride and hexafluoride gives corresponding trioxides. On partial hydrolysis of XeF6 gives xenon oxyfluorides are formed. Xenon oxyfluorides. So on partial hydrolysis of this XeF6, it gives your H2O, it gives your XeOF2 plus your the 4HF is formed. Xenon oxide difluoride is formed. Now here the XeF6 react with 2H2O, that gives XeO2F2 plus here the 2HF is formed. Because here 6 are there, here balance here 2 oxygen atoms and fluor 4HF. Xenon dioxygen difluorides are formed. So these are the some important preparation methods of xenon oxide compounds and xenon oxyfluoride compounds. So are the complete hydrolysis of this xenon fluoride gives corresponding trioxides. Now here on partial hydrolysis of these, it gives corresponding oxyfluorides. Xenon tetroxide preparation and properties are not there, better you remember all these. These are the some important preparation methods of fluorides, xenon oxides, and xenon oxyfluorides. Finally, here are some important points about structures of xenon compounds. We'll discuss one by one. We'll create one important table. Most important table it is. For objective as well as theory, they'll ask any one question based on structures. Structures of xenon compounds. Xenon compounds structures. First, to write the xenon compound structures, first we want xenon atomic number and electronic configuration, number of valence electrons. Already explained electronic configuration. So its general electronic configuration is ns2 and np6 electronic configuration. Now here 54 atomic number, because to the krypton add 18 will get like 54 atomic number. Xenon, its Lewis dot structure is it contain total 8 valence electrons. All these 8 valence electrons are completely paired. This is paired, and it is also paired like these are 8 electrons. So initially at a low temperature in a ground state, all are paired. They do not react with any other atom of an elements. That's why these elements are inert towards the other atom of an elements. That's why they are called inert gases or the noble gases under normal at room temperature. At normal conditions, under normal or at normal conditions, this is less reactive, that is inert. Inert in nature, do not react with the other elements, because are due to its stable octet electronic configuration. Octet EC. This is the reason. But under special conditions, Mr. N. Bartlett conducted so many experiments, explained xenon and Xe and dioxazine both are having comparable ionization energies. So under drastic conditions, yeah, it react with some other elements. It react with other compounds and it forms like XePtEF6, yeah, XeEF2, XeEF4, yeah, XeEF6, yeah, XeO3 or XeO4, yeah, XeOEF2, yeah, XeO2EF2, XeOEF4 are the some important compounds of xenon. So by using this simple analysis to show the bond formation, the electrons are excited from lower energy level to the higher energy level. Now that is NS2, NP5 and ND1 electronic configuration. That is first excited state electronic configuration, like first excited state electronic configuration. Under this, only two unpaired electrons are there. But here the one s orbital, 3p orbital, one d orbital is participated in hybridization. It gives sp3d1 electronic configuration. This is the first excited state electronic configuration. First excited state electronic configuration. Okay. So by using this first excited state electronic configuration, with this one fluorine, with this one fluorine atom is bonded. By using this around sigma 1 2 3 lone pairs are there, like one is sigma, another one is sigma bond is there. That's why sigma, sigma. These two are the lone pairs, and here also lone pair. So we can design the structure of one molecule, XeF2 molecule. We can design like. Once we can observe this fluorine and xenon, and fluorine and xenon is linear because lone pair and lone pair, how much forces are there here? Here also same forces are present here. And here the lone pair repulsive forces are present. Here the two sigma bonds are present, 3 LP electrons are there. Total here the hybrid orbitals are sp3d hybridization is there. Originally sp3d is nothing but 5 are there. Trigonal bipyramidal structure originally, but not a trigonal bipyramidal structure. Generally, by using this, we can take it as a linear structure. Nearly linear means 174 to 180 degrees. Linear. Slightly decrease, not exact 180, 174 degrees are present. That is due to the occurrence of this lone pair repulsion. This bond angle is nearly 174. Like we can create one important table by using this, that is type of the compound, one type of the noble gas compound. Here oxidation state of Xe, oxidation state. Here the number of LP lone pairs, number of bond pairs. Bond pairs means sigma bonds. Lone pairs and bond pairs. Now here hybridized orbital and hybridization. then its structure or bond angle and hybridization like this. We can create one important table like this. So by using this simple analysis, your first one is XeF2. In this XeF2 oxidation state of Xe, your fluorine is -1 into 2 -2 compulsory, that is +2. So oxidation state is +2. Yeah, the lone pair of electrons. Here, how many lone pairs? Not electron pairs. How many means 3 pairs. How many bond pairs means sigma bonds are 2. Hybrid orbitals are 5. That is hybridization is sp3d. Its structure is we can take as like this is the structure. Here lone pairs like 3 lone pairs are there. This is the complete story about this one molecule like here 174 degrees bond angle. Geometry is a linear geometry. This is, even though it is sp3d hybridization. Can you write? Can you guess it? Next example, XeF4 Xenon Tetroxide. What is the oxidation state? What is the oxidation state of xenon? Yeah, -1 into 4, -4. Compulsory for xenon +4. Oxidation state is +4. How many lone pairs are there? Total how many pairs? 4 pairs, 8 electrons. Out of 8 electrons, how many fluoride ions are there here? 4. 4 fluoride ions means we want 2 pairs. 2 pairs means your lone pairs are 2. Bond pairs are 4. Hybridization is sp3d2. Why it is sp3d2? See here, your 2 fluorine atoms means first excited state. 4 fluorine atoms are there. We want a second excited state. Second means from here excite electron up to here. This is the 4 and this is 2. That's why sp3d2 hybridization. Originally, if it is sp3d2, its geometry is octahedral, but not octahedral. It's a square planar geometry. Because around the xenon, 2 lone pairs are there. One is like we can take like this, another one is like this. Now these 4 bonds are with this, like it is a square planar structure. This is the square planar. So our sp3d3 bond geometry is square planar geometry. Then bond angle is 90 degrees. Okay. So in this way, we can design complete all these structures of xenon compounds. See here, xenon hexafluoride. Next one is xenon hexafluoride. Sorry, hexafluoride. Yeah, -1 into 6, -1 into 6, -6. That's why you're +6. So oxidation state is +6. How many lone pairs are there? Means only 1 lone pair. Because total around xenon 8 electrons are there. Out of 8, 6 are bonded means here these 6 are participated. 3 pairs are participated. Only 1 is a lone pair. That's why here third excited state required. This is excites up to here. Now here NP3 and ND3, that is NP3 and like ND3, like sp3d3. Here number of bond pairs, how many means 6 bond pairs, sigma bonds. Now its geometry is sp3d3 hybridization is there. Now originally sp3d2 means octahedral. Here sp3d3 is nothing but pentagonal bipyramidal, but not pentagonal. distorted octahedral structure. Because here Xe, around Xe, first here the 6 fluorine atoms are bonded, like it is F, 6 sigma bonds with fluorine are formed. Now this is the like octahedral shape like this, octahedral geometry. But here one lone pair is there, that lone pair present either, listen here, either maybe here or here or here, anywhere like this, it is lone pair is present. That's why this is distorted octahedral structure it is. Like your bond angles are 144 degrees and nearly 70 degrees are present. 70 to 90, 90 degrees are present in these distorted octahedral structures. Like Xe, F2, Xe, F4, Xe, F6 structures. So we can create like this number of lone pairs, bond pair, hybrid orbitals and hybridization structures are very, very important. Okay, we can manage some more examples like XeO3, XeO4 like. Okay, I'll write remaining 2 to 3 important examples. Listen. So here XeO3 is there, Xenon Tetroxide. Originally, it is an explosive compound. It is explosive oxide, explosive compound of oxides of xenon compound. Xenon compound. Now, in this xenon tetroxide, like Xe, around xenon, 4 pairs are there. Among these 4 pairs, one is lone pair, remaining 3 are bonded with oxygen like this. One double bond is connected with oxygen like. Now here the sigma bonds are 1, 2, 3 sigma bonds are there. One lone pair is there. This is the LP, a lone pair of electrons. Sigma bonds are 3 are there. Pi bonds are here, 3 pi bonds are there. Now in this case, oxygen is -2 into 3 -6. Compulsory, it is +6 oxidation state. So for this oxidation state is +6. And here the number of LP lone pairs 1. Here the bond to pairs. Bond to pairs means here the 3 sigma bonds and 3 pi bonds are present. So to get the hybridized orbitals, these sigma bonds and lone pairs only involved. That's why hybrid orbitals are here 1 plus 3, that is 4, that is sp3 hybridization. If it is sp3, geometry is not a tetrahedral, its geometry is pyramidal structure. Why it is pyramidal structure means based on your valence shell electron pair repulsion theory, like valence shell electron pair repulsion theory, based on their LP and BP repulsions, its geometry changes from tetrahedral to a pyramidal structure. Now here lone pair and bond pair repulsive forces are there. Pyramidal means 107 degrees are there, but here slightly changed nearly 104 degrees. It's a bond angle. So here by using XeO3, finally a number of sigma bonds, pi bonds, oxidation state and hybridization and geometry of the molecule anyone will ask will complete in this periodic in this given table continuously. Next one is XeO4 like xenon tetroxide. Also highly explosive compound, oxides of xenon, not given in our textbook. Anyhow, here around xenon, lone pairs are 4 are there, 4 oxygen atoms are connected with one xenon. Here sigma bonds are 4 sigma bonds and 4 pi bonds are present here. Lone pairs, there is no lone pairs, LP is equals to 0. Sigma bonds are bond pairs, sigma bonds are 4 sigma bonds, and here the pi bonds are also 4 are there, 4 pi bonds. So based on this number of lone pairs, bond pairs, 0 plus 4 that is equals to 4, that is sp3 hybridization. sp3 is nothing but it is in a tetrahedral structure. Why is it tetrahedral is nothing but there is no lone pair and bond pair repulsions. Direct all are means sigma bonds only present. That's why tetrahedrally arranged. Bond angle is 109 degrees 28 minutes. So its bond angle is 109 degrees 28 minutes are present. Like we can create structures in the number of lone pairs and bond pair, number of sigma bonds, pi bonds, oxidation state, and bond angles structures we can easily design by using valence electrons and how many monovalented and divalented atoms are bonded with xenon. Guess it right for this XeOF2 structure. Please try to get its structure. XeOF2. One is one is bivalent, another one is mono. Two are the monovalented atoms are there. Around xenon here, the two fluorine atoms are there bonded with this fluorines like, and remaining three unpaired, three lone pairs are there among these three. Now this is with the oxygen, one pi bond. Remaining are the lone pairs. Sigma bonds are 1, 2, 3 sigma bond and 1 pi bond. Here the lone pairs, these are 2 lone pairs are there. That's why hybrid orbitals are here. Sigma bonds are 3 sigma bonds and 2 LP lone pairs. Total 5 are there. 5 means sp3d hybridization for this. sp3d is nothing but trigonal pyramidal structure originally, but its structure is based on just like PCl5 structure it is. Yeah, PCl5 like 5 are there around these sp3d like bipyramidal structures, but here in this case due to the presence of this lone pairs and bond pair repulsions, by using this it contain like bent or T-shaped structure. This bent or T-shaped structure also called seesaw structure, already explained to you in 16th group elements. Seesaw structure. Like here XeOF4 also, XeOF4. Here also around Xe monovalented are 4 are there like 4, and one is a lone pair is there, another one is pi bonds, like it is a square pyramidal structure it is. Now the sigma bonds are 1, 2, 3, 4, 5 with the lone pair 6 are there. So the xenon undergoes sp3d2 hybridization. Because sigma bonds 1, 2, 3, 4, 5 and 1 pi bond and 1 lone pair is there. So the sigma bonds are 5 are there, LP is equals to 1, total 6 are there. That's why it is a sp3d2 hybridization. Its geometry is not octahedral. Its geometry is a square pyramidal structure. Square pyramidal structure it is. Very, very important structures all these. But you concentrate on this. Maybe they'll ask anyone, oxidation state, lone pairs, bond pairs, geometries, hybridization, everything. Make even flow chart one table for all these. Your oxidation state is -2, -4. This is the +6. Your -2, its oxidation state is +4. Okay. Last, only simple topic, that is uses of noble gases. I'll give the simple uses about noble gases, and in our textbook also created a very simple 1 or 2 uses, important uses. But you remember all those 1 or 2 important uses. Maybe they'll ask 1 mark or the 2 marks. Write any 2 uses of. Last point in this 18th group elements and in P block elements. If you can read complete this P block elements 18th group, will get only 1 mark, not 2 marks. In other cases, maybe if they'll ask in a NEET examination, we'll get 4 marks, 1 question 4 marks. But in PUC theory, only from this we'll get only 1 mark. That is question number 8 or 9 in public. I'll explain right now. Just with one question paper, I'll complete that P block elements questions. Now here uses of noble gases. Use of noble gases. First one is about helium. Now here helium is it is a very light non-inflammable gas. Non-inflammable gas it is. Due to this, light means lightweight. Non-inflammable, cannot catch easily fire. Non-inflammable and lightweight. Due to this reason, it is used in meteorological weather balloons or weather observation balloons. Very, very important. Due to its lightweight, non-inflammable nature, that is filled with balloons or any flights to fly easily towards upward direction. Flight tires also filled with the help of this helium gas because of very light and non-inflammable gas. Now it is generally it is used to produce very low temperature. Very low temperature means nearly 4.2 kelvins. That is gas cool nuclear reactors. In nuclear reactor some apparatus we can use these gas cool nuclear reactors. One of the most important use is it is used by deep sea divers, not drivers. Driver means on road. Divers means water. Diving like sea divers. So for deep sea divers to control the breathing of such a divers, we can use 80% helium and 20% dioxygen, because at a sea level P increases, pressure increases, Without using this 80% helium, oxygen containing nitrogen directly react with hemoglobin. It forms nitroxyhemoglobin. We can't take a proper breath. In such cases, you cannot transport required amount of oxygen through the CNS system. One disease takes place, pains produce a bend. The disease name is called a BNDS, bends. That's why deep sea divers compulsory require this helium and oxygen. And also, your asthma patients, for easy for breathing purpose, they'll use along with helium and oxygen cylinders. They'll use medicinally, it is more useful. And to create the inert atmosphere for all noble gases, generally we can use as to create inert atmosphere. We can use this noble gases, common use of noble gases. Okay. Next one is about neon. About neon. Here generally flash bulbs are decorative purpose, decorative bulbs, and to fill the discharge tubes, we can use this neon. Generally, here argon is used in metallurgical operations. Metallurgical operations are to prevent the oxidation of materials like steel or iron. To prevent the oxidation, we can create in metallurgical operations or in zone refining method. In metallurgy explained in zone refining method, to purify the silicon, impure silicon, to get ultra pure metal like 99.999%. We can use argon as inert gas. That is to create inert atmosphere. Inert atmosphere, we can use this argon. And in gas welding and in some other metallurgical apparatus, we can use this helium. Sorry, argon gas, helium, neon, and argon. Some important uses given. Yeah, krypton and xenon, there is no significant uses. Anyhow, it is argon 85 under the name of a brand name 85. It is used to find out the thickness of the material. Main important thickness of material like plastic or any iron material, we can use this KR85. And here xenon, I can use fluorescent flash bulbs. In fluorescent flash bulb, we can use this xenon. Then finally, radon is a radioactive element, and the treatment of in the treatment of cancer, we can use this radon under the name of radiotherapy. These are some important uses of all these noble gases. Remaining some uses, one or two extra uses, all these uses read from a textbook. Just within 5 minutes, I'll complete one model question paper. I'll show how they are asking questions in examination. So complete P block elements, total in P block elements are 4 groups are there. Among 4 groups, 15th group 3 marks, 16th group 3 marks, 17th group 3 marks, and 18th group only 1 mark. Total 10 marks weightage. Syllabus completed. Okay. Last year it was 2019 March. One more question, that is in part A. In part A, question number is 7. That is, question is given like complete the following. Complete the following question. That is XeEF6 plus H2O gives plus 2HEF given. Then question mark given here. That is 1 mark. So already starting I was very clearly explained to you, to get the out in PUC 70 by 70, each and every one student better read this 18th group elements, because in part A 1 to 10 question there is no choice. In that 1 to 10 from 18th group they'll ask one question. That's why compulsory every student compulsory read this 18th group, only will get 1 mark. That is one question, like simple question they'll ask. You're already balanced here. 2 hydrogens and 2 fluorine atoms are balanced. Remaining 1 oxygen atom and fluorine atoms are 4 are there. That's why answer is XeOEF4. This is answer clear. 1 mark. No need to write this complete. Only in examination, this is the question number 7, part A. Then write this answer and of 1 mark. Then part C. In part C, that is question number 20, question number 21, question number 22. This is from 15th group elements. This is from 16th group elements. This is from 17th group elements. Just I'll give the questions, how they're asking like. 20th question is, mention any 3 anomalous properties of nitrogen. People are generally here, they will write anomalous properties of nitrogen, means they will write regularly due to its small size, high electronegativity, absence of d orbital. They are the conditions to show the anomalous property. Here write any 3 anomalous properties, means 3 points, 3 marks. Means anomalous properties means nitrogen, phosphorus, arsenic, antimony and bismuth. Here nitrogen shows some anomalous properties with the same family members. What are those? One is, so many are there. Among these, nitrogen forms NCl3, not forms pentahalides. One anomalous property. But remaining all are these forms like PCl3 and PCl5, like, because nitrogen covalence is maximum 4, but your covalence is maximum 5. Like, we can create some anomalous properties of nitrogen. Next one is in the manufacture of sulfuric acid from the 16th group. Here write the equations given like SO2 to SO3 reaction. Complete the reaction. One reaction created. Then formation of oleum given. Oleum formation means SO3 plus H2O gives H2S2O7 oleum. 1 mark. And for this SO2 plus O2 gives 2SO3, 2 moles. Vanadium pentoxide and here 2 to 3 and nearly 500 Kelvin's temperature. Clear. 1 mark, 1 mark. Very simple. Then last one is here question number 22 from 17th group elements. Very simple question given from 17th group elements like NH3 plus 3Cl2 gives dash plus 3HCl. Then Cl2 plus F2 at 473 kelvins. Then what is the product? Then this is the 1 mark, 1 mark. Then another one is B question is given structure of HClO4. 1 mark, 1 mark, 1 mark. Your answer is NCl3, clear. Your answer is ClEf, 2 moles, clear. Its structure is around chlorine. Here are the 3 oxygen atoms with a double bond and one is like. This is the structure of perchloric acid. All the points very clearly explained to you. So by observing all these 2019 questions from P block elements, there is no big question. Better you concentrate on only 1 mark and 2 marks questions. That's why to get the all 1 mark and 2 marks questions, better you concentrate and read line to line textbook. Then only we'll get all these for all these questions answers. Otherwise, won't get any clear answers. Okay. Anyhow, P block elements 4 groups successfully completed. Better you read these 4 groups. Then tomorrow we'll start a new lesson. Okay. Anyone? Thank you. Take care.